every operation in math has an inverse, a way of undoing it. And in our exploration of exponential functions, we need to be able to find a way to undo an exponent when our unknown is the exponent itself. In the past, when we've dealt with exponents, it's always been something along the lines of x squared equals 25, where our unknown is the base and we knew the power it was being raised to. So we could undo this type of exponent with a root. Well, what happens when we say when we say 2 to the x power equals 16? Here we know the base, and we have to find the exponent. We can't really say the xth root of 16 equals 2. We have to have another way of undoing it. So what we have is something called logarithms. The way a logarithm works is if we are working with a function or an operation where we have b to the y power equals x, this translates in logarithms to log base b of x equals y. So our bases stay the same. Our answer from before becomes what we're taking the log of, and our exponent is the answer. So back to our original idea of 2 to the x equals 16, this would say log base 2 of 16 equals x. So what power do we raise 2 to get 16? And our answer is 4. And we have a way of being able to evaluate these. Now it is important to remember that when dealing with logarithms, that b has to be greater than 0 and b cannot be 1, because 1 to any power is 1. So let's work on doing some conversions. 5 to the third power equals 125. How can this be rewritten in such a way that we have a logarithmic expression or equation rather than an exponential one? Well, our base will stay the same, so we have log base 5, and we take the log of the answer. So log base 5 of 125 equals 3. Next one, 3 to the negative second equals 1/9. Remember, our negative exponent says we turn the fraction upside down. 3 to the second power is 9, so we end up with 1/9. So what we're going to have here is log base 3 of 1/9 equals a negative 2. 2 to the fifth power equals 32. We keep our base the same, so we have log base 2 of our answer, 32, equals the exponent of 5. Last one, 36 to the 3/2 power equals 216. So we have log base 36 of 216 equals 3/2. So these are all examples of being able to convert from a logarithm or from an exponential equation into a logarithmic one. There's 2 left on here. Pause the video for a couple minutes and try these ones out and see if you come back with the same answers I do. And here are those answers. Log 9 to the third power is 729, so log base 9 of 729 equals 3. Our exponent is the answer. Our bases stay the same. Now log base 8 of 1 over 512 equals negative 3 is the conversion from 8 to the negative third equals 1 over 512. So being able to move back and forth between these is a helpful and useful tool. But what happens as we go through and you see something that says just log? Log of no base equals an item. Well, just like in other types of math, we have certain assumed values. If you don't see something being added, it's assumed to be a 0. If you don't see something being multiplied, it's assumed to be a 1. If you're looking at a root and you don't see an index, we assume the index to be 2. Well, in logarithms, we have the same idea. Our case in logs is that if you don't see a different number being given, you have log of a equals b. This means log base 10 of a equals b. Our common log, and anytime you're using a calculator, the log that it defaults to is a base 10. In our next lesson, we will talk about ways of using technology to be able to change the base and evaluate expressions that have such as log base 3, base 9, base 36, like what we just worked with. But logarithms have many applications in science. The Richter scale for earthquakes is a logarithmic based system. The pH scale, talking about the acidity or base, is a logarithmic function of certain attributes of the elements inside of the item. The decibel scale for volume is a logarithmic section. So when things increase on a decibel scale or a pH scale or a Richter scale, it is an increase of exponential features rather than just a single multiplier. For instance, in the Richter scale, the following formula applies. The log of I1 divided by I2 equals M1 minus M2. And what we have here is I is the intensity of the energy transfer, and M is the magnitude of an earthquake. So the Richter scale is a common log-based scale used to measure the energy output of earthquakes. In 2010, there were 2 major earthquakes that struck the Western Hemisphere. On January 12th, a magnitude 7.0 earthquake struck outside of the Haitian capital Port-au-Prince. Then, about a month and a half later, on February 27th, a magnitude 8.8 earthquake hit central Chile, close to the city of Concepcion. How many times greater energy output was the experienced in Chile as Haiti? So what we have is log of I1 divided by I2 equals our magnitude from the Chilean earthquake of 8.8 minus the magnitude of the Haitian earthquake of 7.0. So log of I1 divided by I2 equals 1.8. 8.8 minus 7.0 is 1.8. So now in order to solve this for our unknown, remember this is a log base 10, and converting back from what we had previously, this means that we're going to take 10 to the 1.8 power will give us that ratio of I1 divided by I2. And when we work that out, we get an answer of about 63.1. So the increase of energy output, the intensity, was about 63 times greater at the Chilean earthquake as opposed to the Haitian. Now some interesting side items. The Haitian earthquake resulted in approximately 316,000 deaths in and around the city of Port-au-Prince, whereas the Chilean earthquake resulted in 525 deaths. So even though there was 63 times more energy output in Chile as in Haiti, and the potential for destruction was much greater, there was more death and destruction that happened in Haiti, and that was due to the types of buildings that were constructed and the preparedness of the people for it. And a major earthquake hadn't hit Haiti in almost 80 years, whereas a major earthquake is felt along the Chilean coast about every 5 to 10, so they were more ready for it. Now, through the process of learning about logarithms, hopefully you've noticed here that a logarithm undoes an exponential equation. So let's take a look at this comparison. In a graphical sense, if we have f of x equals 10 to the x, then when x is 0, we'll make a table of values here. We have x and f of x. If x is 0, anything to 0 power is 1. If x is 1, we get 10. If x is 2, we get 100. If x is negative 1, we get 1/10. So we're going to plot these points on our graph, which has a scale factor, as seen here, of 2. So each line represents 2 in either direction. So we get the following points. And then connecting our points will give us this line, which has a horizontal asymptote at y equals 0, as we studied previously. Now, using this for the new function of g of x equals log of x, not base of x, but log of x, which has a base of 10, we get a table of values, x and g of x, where if x is 0, we get an undefined answer. If it's 1, we get an answer of 0. And if it's 10, we get an answer of 1. So, plotting these points on our graph and connecting the lines, which instead of having a horizontal asymptote at y equals 0, has a vertical asymptote at x equals 0. So these two lines truly do reflect across our identity function of y equals x. And the distance from any point to this line will be the same going in both directions. And you notice that our input and output values are traded on this. So transformations of logarithmic functions are going to follow the same pattern as transformations of other functions. We will have y equals a times log base b of x minus h plus k, which has a vertical asymptote at the value x equals h. So a becomes a multiplier, stretching it vertically. The x minus h will move our value right and left and cause our asymptote to happen, similar idea to having had an axis of symmetry. And our k value will shift our graph vertically by its value. And with this, we can follow simple patterns to graph any logarithmic function. And we will build on the idea of graphing logarithmic functions along with graphing exponentials as we move forward. So make sure you review this and understand the concepts behind logarithmic functions as we move forward in the rest of this chapter.